Good afternoon and welcome to Tasty. So we have two talks today from two visitors. But before that, I wanted to give a quick announcement. So she just told me that we are having a YouTube channel for our department for all the Tasty and the curriculum talks. So it's now just being created, and then she will upload all of the recordings. So hopefully next week we will be able to have that. So let's thank Shikoma for doing that. Talks. So the first talk is going to come from Naadiyah Jagga, who is a graduate student, I think third-year graduate student from York University, working with Adam Wasim. That probably many of you know her already. That she actually runs the Galaxy Journal Club here at 10 a.m. on Thursday. So people should join. But also ask Naadiyah to subscribe to the mailing list and hear about the papers that are being discussed. And I think Naadiyah is working with Adam on a lot of JWST data. So today she's going to tell us about her thesis work. So Naadiyah, please take it away.
All right. Thank you so much for the introduction. I really appreciate it. Today I'm going to talk about Unresolved Photometry. I'm applying that on JWST data, and I'm looking at interested in star maps, mainly the star maps for galaxies over time. So just very quickly about my academic journey. I'm actually from the Netherlands. I did my undergrad and my master's and Leiden Observatory. I did different projects when I was in Leiden. I actually started with stars, then I jumped to planets, and eventually I went to galaxies. And right now I am still sticking with galaxies, but with galaxy observations instead of simulations. So what is spatially resolved photometry? Here you see an image of a galaxy. So usually when we estimate the properties of a galaxy, for example, star maps, we take a single aperture of the galaxy, and then we take all the light within, and then we estimate our galaxy properties for that. However, as you can see, there's like a lot of structure in the galaxy, or like different types of stellar populations. There is gas. You will have most likely a chance of younger stellar populations overshining older stellar population, and therefore you are missing star maps when you try to estimate it with a single aperture. I would also like to emphasize in this image the difference between a Hubble image and a James Webb image, as that is also an integral part of my research. As you can see with Hubble, that is more focused on optical wavelength range. We see more like lower stars, the bulge is very visible. James Webb, which is, we're shifting towards the infrared wavelength, we can see gas or dust, we can see gas filament, and we can look for hints. Or we find redder star populations that would otherwise not be visible. Sorry. All right, so my project fits in the topic of galaxy evolution. I'm focusing on finding accurate measurements of the stellar maps. And the question is, why? So here's a figure on the hill. It's showing the stellar maps versus the red line. It's showing galaxies with different stellar masses, and they form at different times in the universe. You can see that galaxies that were formed earlier, they had a very rapid star formation in the beginning compared to the lower star galaxies, and their whole quick growth is just different. Really depends on when they formed and how massive they are. So we want to have accurate measurements of the stellar masses, because otherwise our stellar mass growth is inaccurate, and therefore our analysis of the evolution of galaxies is incorrect as well. So here's one of the pioneers paper from Sora Sumichi. It is showing on the y-axis unresolved the ratio of the stellar mass for unresolved, so integrated photometry, versus resolved photometry, which is in this case pixel to pixel, versus the specific star formation rate of the galaxy. And it's showing that galaxies with a higher star formation rate seems to have a more underestimation of the stellar mass in unresolved photometry of galaxies. So if this line means that it's the same for unresolved photometry, and means that it means that we are missing stellar mass in these galaxies if we only apply a single aperture. Here is another paper sort of Gucci, but then from 2018. We also showed that there's a clear correlation with the redshift, as the color bar is showing the redshift, and this again the same y and x-axis as the previous plot. However, now you can see that for the galaxies that seem to have a more negative, like the further away from the normal line, or more higher redshift galaxies. So the question is, how would result photometry change, this figure? How would the stellar mass growth curves would be different? So the previous results have been made with observations from Hubble data. We know that Hubble data is mainly in optical wavelength range, so we are missing a lot of information from stars that is behind a dust screen, or from radar stellar populations. So we are certainly missing stellar mass if we only use Hubble data. Therefore, I am also introducing data from the JWST space telescope to push the infrared wavelengths. So again, what I would like to emphasize is really like the difference between Hubble and JWST data. Here we can really see like the gas filaments and like the red data points. And again, like very prominent is the bulge, which is very bright, and like the blue stars, which usually overshine the star populations. So now we have more data and more access to more accurate estimates. So I am part of the data I'm working with is from the CANUCS team. I am a member of CANUCS Solutions for the Canadian Nearest Unbiased Dust Survey, as well as the PI of this CANUCS survey. We are five lens galaxy cluster, clusters, and we're looking at the galaxies behind our lens. So we have even next to like high gravitational lens galaxies. Therefore, we can see quite far to high redshift galaxies. And with each field, there also comes a extra flanking field from the near time. So in total, we have 10 fields, which is quite a lot. All right, so our lens is still with all the filters that we have access to. Other fields are overlapping with Hubble data, so we have both of the fields are observed by Hubble and by JWST. So these are like the filters circled are the filters available in the CANUCS data, and it is covering the optical wavelength range and long wavelengths as well. As for the JWST data we have, not for every field, it depends on the field, of course, but in total we have every one of them and every medium event from the near-term filters. And I would like to emphasize that there's another program that is also basically merged with CANUCS, which is the Technicolor program, where I listen to my supervisors, the PI of, and it is mainly known for observing 3 fields, 3 out of 10 fields for the medium bands and 1 wide band. But it's mainly focused on the medium band and longer wavelengths. The reason why, so medium bands are actually becoming more popular in galaxy research, as it is covering like especially for these medium bands at the right wavelengths, it is basically covering the 4x4, which is the readest available wideband filter. However, with the medium bands, is that the wavelength range is smaller, so you have less background coming in. therefore it should be less noisy if you use the medium band. And so if you have an experimental line in a galaxy, for example, you can see that in a medium band more easily. So this is an example of the importance of using medium bands for the stellar mass density. This is a plot from Sam, from another PhD student in the research group. Medium bands, so the white band stands for white bands are only used to estimate the stellar mass. And if it says medium bands in a purple square, it means that it's white band and medium band. And it's showing that at the higher redshift, that if you only use white band, the stellar mass density is overestimated as you have, like intra-cluster light coming from the background, and you are only applying filters that have a very wide wavelength range. So use the medium bands. All right. So how do we actually estimate the stellar mass and other properties? Just for those who are not familiar, I'm going to very quickly go through spectral energy distribution fitting. So we have a galaxy, and the galaxy consists of different types of stars, like constellations, gas, dust. This is just, an example. It started with a single step population model, which means that you have stars with this from at the same time that have the same metallicity, same atomicity, and they depend on the usual mass function, isotopes, and stellar spectrum. However, a galaxy is a series of single step population models as it has a star formation history. So you have a chemical evolution as well, and when there's star formation, there's density. So all of that together will be composite star population model, which is representing a galaxy. I would also like to emphasize the effect dust. If dust is present in a galaxy, you can see that the rare wavelengths, the light is much brighter rare wavelength as the photons interact with the dust before they penetrate the dust and then hit the telescope. Yes, so keep that in mind. So as far as star formation history, usually a simple star population model is used. That is probably very common in research, but there's a lot of discussion that it's obviously not accurate, especially like the tau model, the delayed tau model, have been used, but this is not accurate. It's not representing a realistic galaxy. So what I'm implying is I'm using dense basis. That is one of a few codes that is applying a non-parametric star formation history. As you can see, down at the bottom, it is showing star formation history, which is clearly not a parametric function. How it works is that you insert data points, and then it finds a fit. And then the star formation history is defined by when the galaxy would have formed 25%, 50%, and 75% of the galaxy. And that's how the star formation history, non-parametric history is reconstructed. Okay, so now we know we estimate the stellar mass, and we know why we want to apply spatially resolved photometry. So now is the question, how do we do that? So you want to create a tessellation of the galaxies. This is just an example where you can see that each thing should have an equal cyclical noise ratio because you want to treat the galaxy uniform. And one bit can contain more pixels. So essentially you can see that the bins are smaller because usually it's brighter in the center, therefore it's smaller in the center, and then towards the edge of the galaxy where the signal to noise ratio is usually lower, the bins become larger. So this is an example of two of my galaxies where I apply a not a precise segmentation of the galaxy to estimate my stellar mass, but I apply a photometry. That's why you see an LS in the form of the galaxy. You can see the smaller data bits center and then like bare patches, which is probably I assume the background near the edge. Yeah, so I applied this on their redshifts filter as some traces instead of max. And here is a so here are a few results from Spatially Resolved Photometry. This one is by Sung. And I really like to emphasize that it's showing bias versus unresolved versus resolved photometry as a function of redshift. And the only thing I would like to emphasize with there is that they're showing that you need to add filters to estimate, to apply for resolved photometry. Otherwise, your bias between unresolved and resolved photometry they only use the Google filters, which is the margin curve. So if you want to apply spatial resolved photometry, use their better filters. This then is a bigger result from JWST Jagga, which was one of the first papers, result photometry with JWST, and it's showing only 5 redshift galaxies, and it's showing that the result versus integrated photometry, so that the stellar mass is in the result photometry higher, which means that in the integrated photometry, the stellar mass is underestimated. All right, so now to my results. So how is my work different? We have many more filters. In total, we have, I think, like 38 filters, which is a lot and useful to constrain your SD fit because, the more filters and more constraint is more accurate. We have 10 fields in total, which 5 are lens. So we have access to a lot of high redshift galaxies. And I'm also applying a non-parametric star formation history. So this is just the samples, and this is applied with unresolved photometry. It's showing, so this is calculated dense basis. It's showing some sort of direction, and the star formation rate versus the stellar mass in the right panel, with the color bar showing the destination, but take the destination with a grain of salt. Anyways, it is showing that most of my galaxies are in this area. So, like, I would say lower stellar mass. I know they're both are in low and high star formation. And there seems to be a trend with the depths that the dust is mainly with the highest stellar mass is you can see as well here. I would also like to show the UVJ, show my samples with the UVJ diagram. Most of the galaxies are star forming. I did apply the destination here, but the destiny galaxies are already there. So the destiny blue galaxies are here. And these are the 10 fields, 20 to 100 targets, which is more than has been done previously. So now to bias, because we want to know what's the difference between unresolved versus resolved photometry. My definition of the bias is that if it's a negative value, it means that the stellar mass is underestimated in unresolved photometry. So aperture positive means that the stellar mass is overestimated. So here's again, say plot I showed before, but with the color bar, it's now showing the bias. And it seems to be that there's like a trend in the J diagram that the more negative bias is for the dusty blue galaxies. It's not super similar. I hope it's not too bright, by the way. But like the lower massive galaxies have more negative bias as well for, although they're scattered everywhere, but most of the negative bias in the stellar mass are correlated with higher star formation, which is in agreement with the Jimenez and with Sorrent-Silici, who applied it in Naadiyah before. So, what about the redshift? Here is this showing the bias on the y-axis for the redshift. I the data set just in low and high scalar maps, just for like simplicity and to see if there's like you know relation with that. I just would like to, with the color bar showing the star formation rate. I just would like isolate some of the high redshift galaxies. Mainly, I'm interested in the ones that have a negative bias and a high star formation rate. Because now I've seen that there seems to be a trend with there seems to be a trend in bias with stellar mass. But what if we, look closely to the galaxies, like their internal processes? So if we want to analyze our galaxies, what is happening as they're all very unique. So it's hard to draw a conclusion from just one plot. I isolated these galaxies, 27 redshift with a negative bias that are fairly dusty and blue galaxies. So with the result photometry, you can create maps. On the left is showing just an RGB, and then the second panel is the system maps map, and then the third is the destination map, so you would break solve, and then the right panel is showing the star formations of the galaxy. What we can say about the is that the galaxy seems to be like company, which is not very visible in standard maps, which might be just the scaling. And as you can see, there are also like dusty patches, which explain why it would have been might explain why it has a negative bias, and then in a single photon, single aperture, you would miss the stellar mass in these galaxies. Here's another few more. These were hydrogen galaxies, by the way, that are showing like the clumpiness in the dusty galaxies. I wanted to have this talk to, and that's what we next step, to show the confidence of all galaxies and see what's the correlation with the rising stellar mass, and then see if there's the clumpiness has to do with the missing mass problem. The population of Chinese stars. Then the question is, how do these stellar mass curve rows change? And that is my takeaway. Thanks,
Naadiyah, for the talk, and we have some time for one or two questions. Anyone want to take? I'll probably start one. And you mentioned you use both JWST and the holiday. How you can see about the measurement tools. With the only JWST only holiday versus the internet together.
I wouldn't check that, but the whole data, the resolution is all controlled to the same resolution of the JPEG data. It would just mean less data points and less optical wavelength, with a bit more newer, but it should not
How that would actually the stuff is pretty much.
I mean, it would miss blue stars, so you would miss maybe some younger star populations and more star population rate, but basically JWST should be covering most of the same wavelength.
Thanks. Any other question for that? If not, let's say there again and again.